Hello friends, today's lecture we will discuss the problem of diffusion. It is a very important topic for any engineering application because lot of heat treatment which we do in practice in industries, diffusion is one of the most important process which takes place during the any heat treatment process. Okay, so we just want to understand this diffusion phenomena, okay, and we will like to see some of the applications of diffusion process. Fick's first law, what do we mean by Fick's first law and Fick's second law, and a couple of applications or where we use Fick's second law. So I will go through all this subtopic one by one. In terms of application, as I told you that in lot of heat treatment processes, diffusion is a very important process, and one of the processes what we have in industry is called carburization. Okay. So steel is a very well known material which is used in lot of applications, structural applications mainly, and to have higher strength on the surface and hardness on the surface, we do a process called carburization. Okay. So as the name suggests, it involves the diffusion of carbon in steel. Okay. So you may not be knowing this right now, but steel is an alloy, and it is an alloy between iron and carbon. So iron and carbon, okay, make an alloy which is called steel. And carburization means that we want to introduce or increase the carbon percentage only on the surface of the any component, okay, to have more strength and more hardness on the surface. Okay. So the process with which we do this is called carburization. Okay. And you can see the effect of this carburization in this particular microstructure. Okay. You can see that there are more white phases, proportion of white phase is more in this part in the interior of the material, whereas at the surface you see that there are more of dark phases. Okay. I am not right now telling you what is white or light phase or what is dark phase, but at least we can see one thing here, that the dark phase is more here and light phase is more here. That means something has happened at this region which has increased the proportion of the dark phase, and that is because of the carbon increase in carbon percentage, and because of that actually there is more perlitic type of microstructure here. Okay. These things we will see later on. Okay. So at least we can see that one thing is that there is a change in the microstructure, and that is because of the diffusion of carbon through the process called carburization. Another very important area where diffusion is a very important process to understand is how you are going to dispose nuclear waste. Okay. So after you take out the energy from these nuclear materials, okay, by the process of radioactivity, they go into lower atomic number elements, okay, but still after getting some energy out, okay, whatever waste is there, still it is a radioactive waste. That means the radioactivity is still there. So we have to contain this material in such containers that diffusion of this radioactive atom should not take place from inside to the outside atmosphere. Okay. So the thickness of the material or the properties of the material should be such that the diffusion of this particular radioactive element should not be very fast. Okay. It should take a sufficient amount of time. Okay. So by that time the radioactivity of that particular element should come down, okay, and should be dropped to such a level that it is not a hazard to any human or any animal life. Okay. So another very important area where we have to understand the diffusion process of this radioactive element through any material. Okay. Third very important application is in preparation of semiconductors, okay, where through doping of impurities, okay, the silicon is made either P or N junction, and it is done through diffusion process, Okay, the process is shown here, that wherever you want to have the doping that particular part of the silicon, we remove this one layer of insulating layer, okay, so that my material is exposed to any diffusing elements, okay, and that is how you alter the silicon as shown in this blue square here, that because of doping the chemical composition of this particular square has changed, okay, and now it will behave either as a p type semiconductor or n type semiconductor. Okay. So, you can see that the wide variety of application, from a very material which is used in structural application to a material which is used to contain this nuclear waste to a material which is used in a very sophisticated electronic application, okay, and everywhere you have this diffusion phenomena, okay, which is used to understand or which is used to bring about change in the material such that you can use it in an application, okay, where these processes are very important. Okay. Now, we will like to understand the diffusion phenomena, okay, and to understand that, okay, we will right now take the example of interstitial atoms. Okay. So, basically one lattice is there where the host atoms are sitting, okay, and in the interstitial position your another type of atom is sitting. Okay. So, we will call the host atoms as A atoms, okay, and the atoms sitting in the interstitial position, okay, as B atoms. Okay. So, we will like to see that how this particular B atom will diffuse. Okay. Diffuse means it has to jump from this site to the next site, okay, and this problem of diffusion will be considered as a random walk problem. Okay. So, it is a random diffusion. So, there is no we are not kind of forcing the atom to go in particular direction, okay, but this is a random walk problem. Okay. But now in some normal books generally available, some misconception takes place that we assume that the atoms will be diffusing from an area where the concentration is more to an area where the concentration is less. Okay. So, that means along the concentration gradient. Okay. The problem in this idea is that we do not know, or how an atom will know that there is a concentration gradient. Okay. For example, suppose this is the lattice of atoms. Okay. I am just drawing some lattice, okay, and in this lattice in interstitial position, suppose in this location there are more interstitial atoms, okay, and later on the concentration of this interstitial atom is less. Okay. Now, the question is that how these atoms know that there is a concentration gradient there, or there is a less concentration there. Okay. That means how they are going to go and travel to that direction. Okay. How this atom will know that there is a less number of B atoms at this location. Okay. So, an atom cannot know, it does not see what is going or what is beyond beyond a immediate neighborhood. Okay. So, to tackle this problem is what we will call it as a random walk problem. Okay. That I am saying that atom does not know anything. Okay. Only what atom does is that atom jumps from one side to another side. For example, in this slide, okay, you can see this atom is staying in this particular interstitial site. Okay. So, from this site it can jump to this next site, okay, or it can jump to this another interstitial site, or maybe this site or this site, and two sites which are in the this projection, okay, and outside this projection. Okay. There will be 6 positions like this in which it can jump, and we do not know where it is going to jump. Okay. So, taking from this idea, we will try to derive the Fick's first law. Okay. Again, in literature, if you see in some books, they will just say that the flux is proportional to concentration gradient and the proportionality constant is some diffusion coefficient, which is wrong. The equation is right, okay, but this inference of this equation in this form is not right. Okay. So, the idea is that we have to understand this problem, okay, saying that we do not know, or the atom does not know there is a concentration gradient. Okay. Atom is only doing one thing, it is jumping from one side to another side, okay, and it can jump to any side. There is no restriction for it to jump on only one particular direction. Okay. So, when I say that, okay, and there are some assumptions we are taking here, that we are saying concentration is so small of B atoms in this particular alloy, that for any atom there is always going to be an adjacent site which is vacant. Okay. So, concentration gradient has to concentration has to be very small to take this assumption. Okay. So, we are dealing with very dilute alloys. This, and if we do that, then we can say that B atom have equal probability of jumping in the neighboring vacant interstitial site. Okay. So, if all the neighboring sites are empty, then this atom can jump to any site, okay, and the probability is same. Okay. So, from there we will start the derivation for the Fick's first law. Okay. Let us start with this slide. Okay. I have drawn two planes here, plane 1 and plane 2, and we are doing analysis only in these two planes. Okay. And we are defining a jump frequency for this interstitial atom, okay, by phi b jumps per second. Okay. So, phi b jumps per second is the jump frequency. So, now let us see what will be the B atom movement between this plane 1 and 2. Okay. So, as I told you that for each of this interstitial atom there will be 6 free sites, okay, in this particular lattice. If you change the lattice, these numbers will change. Okay. 4 you can see in this plane right now, okay, 1 will be out of plane and 1 will be inside plane. So, there will be 6 sites where it can jump. Okay. So, in terms of probability, I can say that it has 1/6 probability, okay, of jumping from plane 1 to plane 2 in one particular direction. It has only have probability of which is 1/6. Okay. So, there is 1/6 probability of an atom jumping from plane 1 to 2. Okay. So, from 1 to 2, if I want to say that what is the probability, okay, that is 1/6. Okay. Now, suppose if there are n1 atoms of B per meter square of plane 1, okay, if I assume that there are n1 number of atoms, okay, per meter square. So, I will write per meter square, okay, in plane 1, okay. Then flux of atom in 1 second from 1 to 2, what will be the flux of atom from flux of atoms from 1 to 2, okay, that will be given by JB, that is the flux we are defining here, okay, JB equal to 1/6, okay, in the direction of that the probability is 1/6. Phi b is the number of jumps per second an atom does. Okay. So, in plane 1 to 2 it will be 1/6 of phi b. Okay. If it does phi b number of jumps per second, so in a particular direction it will be 1/6 into phi b. Okay. And if there are what is the number of atoms we have in plane 1. Okay. So, that many atoms will jump from plane 1 to plane 2. Okay. This will be the flux. Okay. Now, I can do the same analysis from plane 2 to 1. Okay. So, flux of atoms from 2 to 1, I will again write JB, okay, equal to 1/6, same probability will be there, again jump frequency is same for these atoms also, only thing which will change is how many number of atoms are sitting in plane 2. Okay. So, only those atoms can jump obviously in plane 1. Okay. So, now we have flux from 1 to 2 and we have flux from 2 to 1. So, I can now have that what will be the net flux. Okay. Next flux will be the difference between the two. So, now I will write JB is equal to these things are common. So, 1 by 6 phi b and N1 minus N2. Okay. So, it depends on what is the number of atoms in plane 1 and what is the number of planes in N2. So, now you can start seeing that maybe we are started talking about concentration gradient, okay, because there will be different number of atoms, okay, in plane 1 and plane 2, okay, depending upon their concentration. Okay. So, now I will like to define, okay, the concentration at different planes. Okay. So, I will define a concentration C1 is equal to N1 by alpha. Okay. I think I have not defined the alpha here. The alpha is distance between plane 1 and 2. Okay. That is the distance between plane 1 and 2, and suppose if we are talking about a unit area, okay, then I can say that the concentration, okay, will be given by in plane 1 will be given by N1 by alpha atoms per meter cube, okay, okay, per unit volume. Similarly, I can define the concentration in plane 2 as N2 by alpha. Now, why we are interested in concentration is because when we talk about materials or when we do any calculation, we talk about concentration. Okay. We do not talk about number of atoms, okay, that we do not know, okay, how many number of atoms are there. When we make an alloy, when we try to have measurement of concentration, okay, we get concentration in terms of how many atoms per unit volume are there. Okay. It can be atomic percentage, maybe sometime you express the concentration in terms of weight percentage. So, right now it is atomic percentage and at number of atoms in a given volume, okay, and C2 will be concentration in number of atoms in a given volume, okay, again atoms per meter cube. Okay. So, now I have defined C1 and C2 here. Okay. So, I will use that to define or to change this particular equation here. Okay. So, now equation 3 becomes N1 minus N2 will be written as alpha C1 minus C2. Okay. So, I can replace it here. Okay. So, this equation will become now, this particular equation will become now JB 1 by 6 pi b alpha C1 minus C2. Okay. Now, we will like to bring the concentration gradient as I told you. Okay. So, C1 minus C2 I want to express in terms of concentration gradient. Okay. So, if we want to see, okay, if I want to plot the concentration, okay, so I will plot it like this. This is concentration on y axis, this is x distance. Okay. So, suppose if I take a bar here, okay, a bar here, basically I am finding out the concentration at different points, okay, as a function of x, okay, what is the concentration, and that I have plotted. Okay. So, suppose that plot is coming like this, okay, that is a concentration gradient. Okay. Then and this will be, this concentration gradient can be given by this, the slope of this will be del C by del x. Okay. So, now you have concentration at 2 points C1 and C2, at plane 1 and 2. So, for example, this is C1, this is C2, this is C1, this is C2, this is at plane 1, this is at plane 2, and the distance between these two planes, okay, is equal to alpha, as we said. Okay, alpha is distance between plane 1 and 2. Okay. So, now if I want to define, okay, what is C1 minus C2. So, basically what I will take is I will take the slope multiplied by alpha, that will give me the difference between the two concentrations. So, the delta y will be equal to delta x into the slope, our standard definition. Okay. So, that I will replace here now. So, now JB is equal to, okay, it will be 1 by 6 pi b alpha, and now it will be C1 minus C2 will be alpha into del CB by del x. Okay. And if I take alpha out, it will become 1 by 6 phi b alpha square del Cp by del x. Okay. And now I will say that this is my diffusion coefficient. So, JB will become the diffusion coefficient of B, okay, and okay. So, that is what you usually get, that the flux is proportional to the concentration gradient, okay, and it is multiplied by the diffusion coefficient of atom B, okay, and this is for interstitial diffusion. Okay. So, as you can see that I have taken the slope as a constant slope here. Okay. So, the Fick's first law which you are getting here, okay, this is for steady state condition. Okay. What do we mean by steady state condition is that as a function of time, okay, my concentration of at any point, okay, will remain same and it is not going to change. Okay. So, that is my steady state condition, that there is no build up of concentration as a function of time, okay, and this is what we say is Fick's first law. So, for steady state condition there is a Fick's first law which is given as we have just derived. Okay. I am sorry I did not put the sign here, actually because it is a negative slope you will have a minus sign here and you will get a minus sign here. Okay. And d is given by as you can see on the slide, basically d is d naught exponential minus q by RT. Okay. So, this is my Fick's first law. I am not doing the derivation for the Fick's second law, okay, because I just wanted to bring the flavor of this random walk problem and how we can use that to derive Fick's first law. And there are some misconceptions sometimes you find in book that they do not clearly specify that. Okay. The Fick's second law deals with the non-steady state condition, okay, and in that what do we mean by non-steady state condition is that the flux will change, the concentration at any point will change as a function of time. So, there is a accumulation of atoms or depletion of atoms as the or change in the concentration at a particular point as a function of time. Okay. When you see this particular curve, okay, it is not going to give you change in the concentration at a particular point with the time. Okay. When you will get the non-steady state condition, if in terms of this particular graph I want to see, okay, that I will show you. So, this is for steady state condition. Okay. Okay. For non-steady state condition, okay, the graph will be like this. This is my concentration, this is the distance x. Okay. Let me plot the block here. okay, this distance x, okay, and the graph will be like this. Okay. Now, what does it mean? Okay, if you see as we derived in the Fick's first law, that JB is equal to dB del C by del x. That means my flux of atom is dependent on the concentration gradient, okay, the slope of the curve. Here the slope is constant, okay, that is why it is a steady state condition. Now, here my slope is changing. So, if you see at this point, suppose I want to see at this point and I want to compare it with this point, okay, the slope is something like this, here the slope is like this. Okay. So, here the slope is more, so the flux of atom will be coming more. Okay. So, let us say if this is my plane 1, this is my plane 2, and suppose I draw these two planes here, okay, plane 1, plane 2. So, J1, let me call this as J1, okay, the flux J1 from going from plane 1 towards plane 2, and there is J2 coming out of plane 2. Okay. Now, the slope is more in case of 1 and slope is less in case of 2. So, there will be more flux of atom going from plane 1 and the volume in between, and there is less number of atoms coming out of this volume and going out. Okay. So, now that means if I have more flux coming in, less flux going on between plane 1 and 2, okay, what will happen? There will be an accumulation of atoms, okay, and this accumulation will means that there will be change in the concentration of this particular element as a function of time. So, after some constant interval, if I want to measure what is the concentration here, the concentration will keep changing, whereas in this first case the concentration will remain same, it will not change as a function of time because the slope is constant. Okay. So, Fick's second law deals with the non-steady state condition, okay, and which tells me that there will be change in the concentration as a function of time, okay, and which is the more practical, which has more practical application, okay, because in normal experiments or normal applications, it is always going to be a non-steady state condition. Okay. So, for Fick's second law, this is the equation. As I told you, the concentration will change as a function of time. So, del C by del T is equal to D, and this is the curvature of the curve between the concentration and x. Okay. Del square C by del x square will give you the curvature of the curve between C and x. Okay. So, it will depend on the curvature, okay, and of course, the diffusion coefficient, okay, and the concentration will change as a function of time. Now, there are two applications of these, okay, as I told you, carburization is one, okay, and application of Fick's second law in carburization, the equation which we are going to use, okay. Right now, I am not doing any problems, okay, but we will take up that in our assignments. Okay. So, the change in the concentration as a function of distance and as a function of time, okay, will depend on what is the concentration at the surface of your material, what is the initial concentration of your material, okay, and what is your diffusivity, total time you are exposing your material to that particular element, okay, and what is the distance at which you are trying to find out the concentration. Okay. So, it will depend on all these parameters. Okay. There is another term here coming which is called error function. Okay. So, because these are these type of equations, you do not get a definite integration. Okay. What we do is we use a statistical function which is called error function to find out the solution. Okay. So, that is why we are using this error function here. Okay. You will see this kind of error function in other applications also. I think in heat conduction also you must be having this error function coming into equation. Okay. This is for decarbonization. Okay, the earlier equation was for carbonization. Same thing can happen if you heat treat a material, okay, in a atmosphere where instead of carbon you have some other atmosphere, let us say oxygen. Okay, in normal atmosphere you are doing heat treatment, then what will happen, carbon from inside the material will diffuse out and carbon will react with oxygen and may form carbon monoxide or carbon dioxide, okay, and this carbon will keep on diffusing and you will have a layer on the surface which is having less number of carbon atoms. Okay, so this we call as decarbonization, okay, and this is the solution for that, okay, which you can use to find out how much will be the decarbonized layer. Then one small comment on there is another type of diffusion, okay, we are not doing it because these are the two most important one for a practicing engineer who has a mechanical background, okay, that is why I am not going into some other aspects of diffusion here, okay. I am just giving one last comment on some other type of diffusion which also takes place, which is not interstitial, okay. So it can be substitutional diffusion, okay. And in this there can be two cases, one is where self diffusion of atoms takes place. So you can see that there are at all the lattice point same type of atoms are there and there is a vacancy, okay. So now these atoms, okay, they have a vacant site on which they can jump, okay. So now they are diffusing, okay, you can understand it as a diffusion process. Similarly, again you have a vacancy here in the lattice and there is a substitutional atom is there which is occupying the regular position, okay. So those atoms are called substitutional atoms, okay, and this atom can jump into this vacant site, okay. So this is the two other type of diffusion, okay. In case of interstitial diffusion, the interstitial sites are always present. In case of this diffusion which is dependent on vacancies, you can understand that vacancy is a strong function of temperature, it increases exponentially with temperature. So where you need vacancies, okay, so the diffusion process will depend on both the ability of an atom to jump from one site to another site and there should be creation of vacancies to do that, okay. So this both will come together to have any diffusion. So we use the interstitial diffusion idea first to derive the Fick's first law, and from there we said that you can also get Fick's second law, and we saw that there can be two very important applications of Fick's second law is in finding out what is the time and distance for a carbonization process, okay, or decarbonization process, okay, and what will require if you have a substitutional diffusion. So one can be self diffusion, the same atoms can diffuse if vacancy is there. Another case, a substitutional atom can be there, okay, where you have a vacant site and the diffusion is taking place in that vacant site, okay. So with that I will stop this lecture. Thank you.